Thank you so much. And we actually will talk a little bit more about the least favorite, but probably the most important part and topic for software engineers, which is cybersecurity. And we will talk about the zero trust in satellite software updates. So I'm presenting of SylLab systems alongside with my colleague Layne Merritt, who is joining us online. And we will be talking about the zero trust in satellite software updates, as this is a critical focus area as the number of vehicles are increasing, as well as the hostility and the contested space environment is emerging. So I would like to just start off with the introduction of myself. I am certified information security professional. I've been both on the technical product side and the commercial side, although I promise I will not be selling you today anything. And I would like to pass on to Layne to introduce himself and tell us a little bit more about our journey as SylLab with the zero trust topic.
Great, thanks, Bart, and thanks everybody. Sorry I couldn't be there in Seattle with you. I'm here in Fort Worth, Texas. So I spent a long time in the Army. I was a airplane and helicopter pilot, an experimental test pilot, and then a technology developer where I managed the Army's aviation science and technology portfolio. Then I spent some time in industry as CTO at Elbit America and GM at a small avionics company. Let's go to the next slide and we can introduce SylLab. So SylLab is a small cybersecurity firm. We're based in the Dallas-Fort Worth area. We work a lot with the Department of Defense and supporting industry. We were awarded a small business innovative research contract with AFWorks, which is Air Force, in the area of space communications. We also worked with AFRL, which is the Air Force Research Lab, in their Catalyst Accelerator, which is managed by Mass Challenge. Go to the next slide. We also work with commercial, and FFRDC is federally funded research and development centers. That's the supporting industry, the people that help the government make real what they need in their area of defense and other areas, of course. Okay, now I'm going to pass it back to Bart, and he'll start building our case for secure satellite update process.
Thank you, Layne. And we had excellent presentation earlier this morning. So I treat it also as a continuation of our discussion on updates, especially in our context, is the security of the update processes. So I would like to start back with what is actually zero trust. It has been used, and it's a buzzword, is a keyword for many, but I would like to just go into details of what exactly it means. So in context of satellite updates, it means that there's no implicit trust within any part of the system. So every access request or data exchange must be verified. And one of the slogans used by the US Space Force is to never trust and always verify. And in space satellite systems, what it really means is that every command, a data packet or interaction, whether it is within ground station or between satellites, has to be treated as untrusted until it's verified. And to support this, there are actually a lot of benefits and tangible research on using zero trust within space architecture. So according to NASA simulation, demonstrated that introducing digital signature can reduce unauthorized command attempts by 75%. The US Space Force has also found out in their research that introducing strict access control can reduce the potential impact compromised subsystems by 65%. And there are also other statistics. One of them saying is that introducing modern encryption can, of course, improve the confidentiality as well. So with that in mind is that I also would like to say that a lot of the space vehicles that are currently available, they've been designed in the time that there was no zero trust or any cybersecurity in mind. So there was no approach to secure by design. So this is relatively new. So a lot of these introductions to the space architecture with zero trust, it's still relatively new when it comes to, especially with the update process itself. So why it matters to the update process is because of the fact that update process is very critical to the operation of the satellite. So imagine from a malicious actor perspective, having access to actually deploy something on the satellite or the satellite system, it gives you an open door to compromise the entire satellite architecture. So it's a very critical process that if compromised, it can definitely damage the cybersecurity posture. So with the benefits, when we are introducing zero trust, we are also preventing unauthorized code execution and resilience to the fact if ground control is breached. So if we have this, if we follow this principle of never trust, always verify, is that even though that the ground station is compromised, we know that the satellite will reject malicious attempts to introduce the code itself on satellites. And we also can use the continuous authentication during the transfer, so we get that granularity. And as a real world example is that when Starlink was attacked in 2022 by Russian forces with the jamming, the secure update process restored the functionality over thousands of satellites. So this also emphasized that there's actually a real world scenario where when we are looking at cybersecurity itself, and we look at the compromise itself, patching is the last step, which is very crucial to recovering an asset or recovering a satellite that was compromised. So after we isolated and contained, patching is the one element that is crucial. So it's important that it's secure by design. When we talked about the trends, I would like to talk about two trends when it comes to introducing zero trust. Because zero trust, there's a lot of digital signature integrity checks that needs to be performed in order for the satellite to have that possibility to reject malicious attempts. Digital signature will be impacted by two main of the trends that we will talk about. One of them is post-quantum cryptography, and the other one is legacy systems and security upgrades of the current legacy systems that are flying. So before we go to post-quantum cryptography, I would like to take this step back and explain a little bit more on the current methods that are used to authenticate the software that is being deployed to the satellites. So we have hash-based integrity checks, we have SHA algorithm and any other methods to verify the authenticity of and integrity of it. And then we have digital signatures. So we have RSA, elliptic curve that are mostly commonly used, standardized, and have been used for years. So in the case of hash, it's integrity check. In case of the digital signatures, we are verifying the public key on the satellite. So with the change itself and migration to post-quantum cryptography, if we're looking at the CIA triad with the confidentiality, integrity, availability, the integrity part, it will be the most impacted by the change because of the fact that as soon as we have powerful enough quantum computer, the algorithms that are currently providing digital signatures will be the most impacted. So with the timeline itself, this effort has been going on for more than 15 years. I have listed out from 2021 when things accelerated, and we do have currently the transition going on and timeline from the government to impose standards and a mandate requiring all the government agencies to move to post-quantum cryptography, also all the defense contractors as well, and commercial companies will follow as well. So with the threat itself, why we are doing this is because as soon as we have powerful quantum computer, the digital signatures on the secure boot or on the software update will be compromised. So that's why it's important to move to these new standards. So with that in mind, the timeline itself, when we talk about the transition from the traditional to post-quantum cryptographic algorithms, it has been listed out by the CNSA 2.0, which is an upgrade from CNSA 1.0, explaining the commercial use of algorithms for certain functions like digital signature. So one of the first areas that will be impacted by this change is software and firmware signing. So that's why we're talking about this today. So from 2025 until 2030, they expect already the change to be happening. I also have to mention that the last cryptographic change that happened took more than 15 years. So there's not a lot of time for the things to change. However, it is a mandate already, so hopefully the changes will be coming. But not only a mandate itself, but we also have some of the community, cryptographic community efforts to release open source libraries that are implementing these algorithms that are standardized, or they were competing for the standardization. And one of them I would like to recommend is openquantumsafe.org, that can be accessed and tested and used as a test bed for any type of applications that you're currently running to evaluate, and it's open to public, and you have a lot of implementations of these post-quantum algorithms. So with that in mind, moving to what exactly has been standardized by NIST is that we have key encapsulation, we have digital signature, and a hash-based digital signature as well. So there were 3 standards released. So it's FIPS from 203 to 205. And these are mainly addressing the most urgent changes. So we have, instead of using Diffie-Hellman key exchange, we will be using the key encapsulations by Crystal Skyber. And we also will be using some of the algorithms that were also standardized for digital signature and hash-based digital signature. So I would like to pass to Layne to talk a little bit more about the legacy systems and the security upgrades.
So legacy systems are especially challenging as a use case because they weren't built with a lot of software. They weren't built with a lot of processing power. You can see there listed the modest resources that the NASA's Voyager probes have. Even the original space shuttles had less memory than today's simplest handheld calculators. They just did things differently, and they were very, very efficient with their code. But these satellites were not designed. They had no pre-existing security hooks. They weren't designed to be updated very often. And when they were, they pretty much went offline until the whole thing was completed. And if something went wrong, then they were offline for even longer. And we don't want that to happen these days, especially if you're doing a whole constellation of similar satellites. They also have very low bandwidth communications, and they don't communicate all the time, right? So you have to be very efficient with what you do. And they didn't document things as well, and just with the passing of time, a lot of the documentation just isn't available, got lost or misplaced, whatever the case may be. So now I'll pass it back to Bart, and he'll talk about how we might solve that problem with the legacy systems.
Thank you so much, Layne, for that introduction. So some of the things that we have researched on what can be available when addressing these issues when it comes to legacy systems is to introduce additional security protocols on the ground station, so two-man control or any type of methods that can be on the cybersecurity and access control side that can be implemented to enhance the security itself. When it comes to protocol emulation gateways, we have found out that there opportunities there as well to translate the modern secure commands into legacy systems expected by the satellite. And we have also what is called micro patching, micro updates. That has been also quite a trend as well when it comes to especially space vehicles, when instead of deploying the whole image itself or very, very heavy on the satellite, especially for the constrained satellites, we have ability to introduce one line of code, or even in case of Voyager 1, that was one bit that helped to resolve the glitch when it comes to telemetry issue. So there's definitely ability to minimize the impact of the update itself when it's limited to a single line of code, or if it's limited to one particular area of the code, not necessarily the whole image itself. So that patching has been, at least on the research side, quite well documented and tested. So to summarize our presentation, we talked about zero trust for satellite update processes. So we talked about digital signature and why it's important for all the updates to be digitally signed, so that you have the ability to trace down on what actually has happened, and the ability for the satellite to reject a potential malicious injection. And with the principle of never trust, always verify, and the ability to ensure resilience. And some of the trends we talk about today were post-quantum cryptography, worth highlighting, as well as some of the trends of working with legacy systems. So thank you so much for your time. I would like to just say that we're a company based out of Dallas Fort Worth, providing beyond Earth security. And for collaboration opportunities, you can contact me via email. And thank you so much for your time.
Thank you, Bart.
I'm going to take the first question. This may be a massively dumb question. Quantum computers 2030. We have quantum safe algorithms now. How do we know they're quantum safe?
So because they were mathematically proven to be resilient against a possible threat of quantum computers. So mathematically, the RSA is built on prime factorization. When it comes to these new algorithms, they're lattice-based. So there's mathematical proof that they can address what Shor's algorithm has proven, that if viable quantum computers can break the current encryption. So that has been identified in specific methods, lattice being the one leading, but also other methods were used. And they're being also, so we have, for example, recently it was announced that code-based signature, or code-based, not signature, but code-based key encapsulation will be possibly standardized in 2026. So the community is still working on that, but we already at least have these 3 standards that we believe that they're quantum safe.
Question here.
Hello. I think you mentioned the SDLS. And with respect to quantum, do you think it is safer now, or it will need to be updated?
So that's an excellent question. When it comes to the protocols currently being used, these protocols usually use what is called symmetric encryption, so, or authenticated encryption. So that's actually a very good question. So according to Grover's algorithm, all the security, the key security is being halved when it comes to quantum computers. So if we are using anything above, if we are using 256, we will get 128. So anything above 100 is considered, well, 128 is considered secure. So if you are using, if you see that there's AES-256 implemented for the symmetric encryption, you just have to check if what has been used for exchange the keys, because that's where the vulnerable part is.
And one more?
I have another trend here. Are you working on supply chain attacks, prevention of supply chain attacks?
Yes, that
I
has.
think- Go ahead, please. Yeah,
Yeah.
thank you.
Thank you. So supply chain attacks, exactly, that's a really good point, because when we talked about updates, we have to talk about the main origin. As we had in the earlier presentation today, the origin of it is a CDCI pipeline. So starting from there, if you have a signature that is valid and can be somehow authenticated on satellite, you can trace down the different aspects of the software supply chain. When it comes to other methods, of course, having hardware supply chain implemented is very difficult. Microsoft has been trying to do that for many years, and I have not succeeded in that. But the main principle is that if you have a digital signature at the core of your software development, and you can trace it all the way to the satellite, there's some security of the supply chain as well.
Thank you very much, Bart.
Thank you so much. Thank you, Layne.